right, welcome back. We're going to start talking about our polynomial functions, okay? And polynomial functions are anything that will have this kind of general form. Ax to the n plus bx to the n minus 1, n being an integer, decreasing powers of the polynomial, okay? And so there's the form again, and examples. Okay, and the names given to different polynomials depending upon the degree being the highest exponent for the polynomial. Typically, they're written in descending powers, but they don't need to, so you got to watch out in the event they're not written in descending powers. We all know quadratics, cubics, fourth power are quartics, but we generally just call them fourth degree polynomials and the like, okay? In terms of polynomials, the biggest thing we're going to be concerned about is the graph. And for our purposes, for most purposes, okay, the line of dissertation between polynomials is going to become whether they're even or odd powers. So we're certainly going to classify them, and it's easy enough to determine, and we're going to talk about them in terms of their powers, okay? So the degree of the function will determine the maximum number of x-intercepts, okay? A fifth degree polynomial could have 5 intercepts, but it could have less than 5, although as we'll see it must have at least 1. A quadratic, as we know, will have 2 intercepts, but it could have 1 or none. Okay, so let's continue. All right. We'll also address what we call the turning points, okay, and we'll see them once we start looking at the graph. So the things that we want to go through when we're graphing polynomials are some of the things that we've already looked at in terms of simpler expressions. Determining the y-intercept obviously is always easy enough to do. It's just setting x equals 0. That's usually available for you. A lot of times the polynomials are factorable. The factors can help you find the x-intercept. Multiplicities, we're going to talk about what they are. They're single x-intercepts, but they're produced by higher powered factors. Okay. The end behavior, we're going to have a approach that we use calculus to name the end behaviors. Okay, and that's going to be different depending upon whether the polynomials are even or odd. Okay, also don't forget aspects of symmetry, which can also be of a great aid when having the graph. Okay, so, and with the symmetry, as we should recall, a lot of people get those confused. Okay, the difference between symmetry about the y-axis. Of course, we won't have to worry about symmetry about the x-axis, otherwise it wouldn't be considered a function, but we do often look for symmetry about the origin, okay? And we have a lot of times this the even power polynomials will have that symmetry about the y-axis, okay? And in some of the odd powered polynomials will have that symmetry about the origin, so we'll have to recall that as well. Side tables may come in handy. Although as you learn more and more about the polynomials, they'll have less and less of a need to deal with a side table. Okay. All right. So let's go through an example of constructing a graph. So here we have this cubic polynomial. Obviously, the y-intercept is right there, right, for the picking at -12. Okay. It will factor. We can factor it by grouping. I'm going to split it apart, pull out the common factors from each of the two groups, and then we're going to refactor this again. And in factoring that, we see that it offers us 3 x-intercepts at 2, -2, and -3. The sign table can be generated, and so we'll run through that here. And the sign table listing the factors on along the left-hand side. Okay, and the intercepts down along the bottom in the same order as if on a number line. Okay, generate the sign table, and then the end result is of course what we're interested in, and that is going from negative to positive, negative to positive. And the graph then of course would find us having intercepts at these three locations, -3, -2, and 2, and then the graph going through them, rising up from the negative area, then going positive, then going negative again, and here's our graph. So here we are, negative from negative infinity up to -3, then we dip positive, then we dip negative again, just in line with the sign table as you can see there. Okay, so let's talk more. Let's start talking about the even powers. Okay, even power polynomials. All right, here's our examples, and then we'll talk about them. Okay, all even power polynomials have a definitive shape. Okay, the definitive shape says that both ends either go up or both ends go down. Okay, both ends are going up, both ends are going down, both ends are going up, both ends are going down. Okay, that will always be the case with any even power polynomial, no matter whether it's a squared, a quadratic, fourth power. In this case, this of course would be a 2, 4, 6 power polynomial, as well as another 6 power polynomial. Okay, we had mentioned multiplicities. Here are the multiplicities. Here, the multiplicity comes at 0, and at -2, and at +1. So the multiplicity there shows that it's not going through, it's just touching that intercept, it's being tangent to that intercept at those three locations. Okay, and the same thing over here. The statement about the even power polynomials, once we determine that it's even, easy enough to do by the highest power again. Okay, we look at what's the end behavior. Both ends rise or both ends fall. Okay, both ends rise when the coefficient to the highest power term is positive. Both ends fall when the coefficient to the highest power term is negative. Okay, the language of calculus says this is read: the limit as x goes to negative infinity is infinity, and the limit as x goes to positive infinity is infinity. So in other words, okay, let's look at this as an example. As we move further out in the negative infinity, our function just continues to rise and rise and rise towards positive infinity. As we move out towards, okay, positive infinity, again, the function, the graph keeps on rising and rising, so it approaches positive infinity. When we have the first lead-off term being negative, the a term being negative, then that will have the opposite effect, both ends dropping, as is the case with the example here, the second and the fourth example. Okay, whereas you can see, as this explains, as we move into negative infinity on the function drops off into negative infinity for the y values. Okay, and likewise, as we move towards positive infinity, the function drops off into negative infinity. This is the language of the calculus, but we might as well get exposed to it now. So it's the best way of categorizing these things. Let's look at odd power polynomials. Okay, in terms of their end behavior. Okay, here's a couple examples. And let's discuss them. Okay, odd power. Okay, we have one end falling, one end rising. Okay, one end rising, one end falling. Always the case. One end ends up, one end goes down. Okay, that would be the case with the odd power. Okay, generalization: when the lead-off term is negative and when the lead-off term is positive, we have two different types of behavior, characterized by lead-off term being positive. Okay, the left end falls down, the right end rises up. Lead-off term being positive, the left end falls down, the right end continues to go up. Okay, With the leadoff term being negative, the opposite. The left end goes up, the right end goes down. So the language of the calculus, allowing us to say that in a more precise fashion. Okay, for odd power polynomials with leadoff positives, okay, as we move towards negative infinity, the function just drops down to negative infinity. As we move towards positive infinity, the function just continues to rise towards positive infinity. And just the opposite for the leadoff term being negative. Moving towards negative infinity, we're talking about the left hand and behavior, it will continue to rise towards positive infinity. Moving on the odd powered polynomial function with leadoff term negative, as we move towards the right hand, moving towards positive infinity, the function will drop off, approaching negative infinity. That is how we categorize what we call the end behavior of the polynomials. Okay, and that does it for this